Good morning, everyone. For me, I'm Johannes Kaiser. I'm one of the mentors for the fire forecasting project. And first of all, I'd like to take the opportunity to thank ECMWF for setting up this program, providing the infrastructure, the computing infrastructure, but also the meeting infrastructure for people here, and to Atina and Esperanza for all the support and running. So that has been really essential that you two have been there along the way throughout. Then Robert will take over. Timo is also in the room from the forecasting team, and the other two people who are involved are Eva Maria Metz and Christopher Winkels, who unfortunately cannot join us today in person here. Let's get going. This project is called fire forecasting. So we are talking about wildfires. Why do we talk about wildfires in our context? We see that the smoke emitted from wildfires has a very large impact on air quality. And I imagine that every one of you this summer has seen this on the news in one form or another again and again and again. And particularly dominant were the wildfires in Canada this summer, but also Europe had some really extreme wildfire events, for example, in Greece. Stein mentioned the Atmosphere Copernicus Monitoring Service, CAMS. This is providing, besides many other things, but as core products, 5-day forecasts for atmospheric composition globally and for air quality for the European domain. And here's an example from this forecast from the webpage, which is the forecast of PM 2.5 for Bologna for this week, Tuesday to Friday. And you can see the color codes are thresholds determined by the European Environmental Agency. You see that we are in Bologna in a safe space this week. This is, there are no fires at the moment, but these PM levels can be affected by smoke from wildfires, of course. And that's what we're looking at in the project. So the smoke we need to, in order to do the forecast properly, we need to observe the fires from space and then determine from the observations where there are fires, how much smoke is being emitted, and put those in the model so that then we see in the forecast for Bologna whether there's a big plume coming through and people can adapt their behavior in case of really bad events. What is currently being done is we see the observed fires and then we use a 5-day persistence of the fire source. And here's an example of forecasts from the regional fire system for August in Greece here. That is the situation in terms of smoke, AOD, optical depth. So you can say how much smoke there is in the air. Over Greece on the 23rd of August, and that's the situation that was observed. And then there is a forecast initiated on the 25th, 26th, 27th, up to 27. And you could see that the smoke gets affected, but all the time the source stays at the one point there. And that may not be realistic because we know when there's a fire, it's going to extinguish eventually. So we are really producing false alarms with the system at the moment. And here the team comes in and they have developed a method with which I'm confident with the results that we will be able to reduce the number of false alarms within, say, the next half or full year of our CAMS forecast. So, and with that, I hand over to Robert. Thank you.
Yes, as Johannes mentioned, the current approach is persistent. So the assumption is that the fire for the next 5 days stays exactly the same as currently. And we want to forecast the wildfire intensity. So here you can see an example plot for how the fire intensity is normally measured between fire-related power, which is measured by satellites. And we want to use the GFAS, global. That's a step back. Yes, and we want to use the simulated system GFAS, which uses a satellite information, simulates them, and we want to use them to forecast the wildfire intensity for GFAS, as explained. So we made the problem a little bit smaller because we started from the forecast for 1 day, 24 hours, based on the previous 24 hours. We use as an input for the forecast the fire from the previous day, but want to predict the fire for the next day. But we also use as an input the meteorological parameters from the previous day and the forecast of the meteorological parameters. And then we want to train the model of it and want to predict the fire. And the projection should be better than systems, because that's the kind of approach. That's what we need to do. So in principle, it looks like this, that we use the animation would not work right. But so we have in green, you see the IFS, which is the integrated forecast from the ECMWF, which concludes the meteorological parameter for the past 24 hours and the next 24 hours. And we have GFAS with the past 24 hours of fire rated power, which we feed into the model. And then we have the prediction, which produces the next 24 hours and is compared with the GFAS data for the next 24 hours. And that's the method how we train the model to predict wildfires. So how do we select the meteorological parameters? We looked at the correlation of some parameters from the data set, and we choose actually 5 parameter variables. Small typo. We choose the volumetric soil water layer in the upper layer, the 10-meter absolute wind velocity, the skin surface temperature, fire rate of power, and the uncertainty of the fire rate of power. Why do we choose them? You can see here in the plot the correlation for some parameters. Those are more than are listed here because we have relative humidity, volumetric soil water layer, and total precipitation rate. And the plot, you can see here that volumetric soil water layer 1 has the highest correlation and kind of captures the physical relation between water and fire. So as the first step for the training, to make the problem a little bit simpler, we choose the volumetric soil water layer because from this information, we assume that has the most influence, and we want to use physical parameters so that our model does not learn to tries to predict the fire from maybe some correlation in the structure of the data or some arbitrary parameters that might be correlated, but from the physical parameters. For the area, we choose the latitude band between 30 and 70 degrees latitude, so that we have North America and also Europe and Northern Asia. And for the time period, we have the periods from 2020 to 2022, from May to October, and from this year from May to June for the training, which is the case. We also applied our model to from data from this year from wildfires from July to August in Greece and Canada. An example. For the resolution, we have a resolution of 0.5 times 0.5 degrees and a temporal resolution, which is hourly. The training for one model took around 30 minutes on an NVIDIA A100, which was supplied by resources from the ECMWF. But because we used hyperparameter training to find the best parameters for a network experience plot, of course, the total training time to find a good model is larger, but for a single model, it takes 30 minutes. And the prediction is quite fast for one day. Yeah, there was some animation. You can see the relics of that here. Yeah, we tested the current approach with persistence as a baseline, of course, because that's what we want to be. But we thought also about let's not just dive into neural networks, but test some simpler models. Maybe let's see, maybe we don't need neural networks. Maybe it works well already with the linear regression or regression tree. Just a basic concept. Linear regression is just a linear model. I was walking out the screen. And the regression tree is conceptually you divide the input space and then look for events that are similar to predict them with what you have in the training set. So it's in this case not important, but those are simpler models that don't have quite the complexity of a neural network, so they're not as flexible fit to the data. And then we use neural networks. We actually use an ensemble of 5 identical neural networks. The idea behind that was that we have a easy way to get uncertainty prediction for our results because we use an ensemble and we can use a standard prediction. So let's look at the results of all 4 methods. So on the left side, you see a table with the results. We have 3 metrics in total. So we have the mean average error, the root mean squared error, and the correlation. In the first line, we have the persistence, which gives the baseline. And you don't have to look at the exact values from the other 2 models, only check the neural network ensemble. And if you compare each metric, you can see that it improves quite by a lot. The prediction, what would actually be expected, what we hope for. And on the right side, you can see a plot of the phi-rated power. So it's again the 48 time steps. So in black, do you see my mouse? Yes. You can see here the measurement, and then the measurement goes down here. So it reduces. And you can see here in red is the neural network, and you can see that it follows the measurement, whereas the spread from the other models is quite huge. So you can also see in a small example that the neural network does something better than the other models. But let's look into detail into 2 small examples. And one has to say for this, it's a neural network. We did not test if it's physically reasonable. We just looked at small examples. Maybe this might be a step for the future. We check if it's physically visible. So here's an example forecast of the neural network ensemble. Again, 48 hours. We have the 24 hours, the past day and the next day. We have in black the measurements with the uncertainty of the measurements. And in red, we have the prediction of the neural network ensemble with in lighter shaded red, the standard deviation of the ensemble. And we have 3 more variables. We have the volumetric soil water layer in green, in dotted green. We have the temperature in blue and the wind in gray. And one can see here, first, there's a diurnal cycle of the temperature. So you can see here, it's the afternoon peak of the temperature and the lowest point in the night. And one can see here that the volumetric soil water layer goes down during the 48 hours, and the wind somewhat varies and goes up towards the end. One can see that the fire on the second day is slightly larger, but the ensemble of neural networks doesn't really capture it, but it shows the same diurnal cycle. So we see here that it's very low, which is during the night, and then increases again during the day, but not as strong. And another example here, it's again, same colors, but different measurements. So we have here again the measurements in black. It goes up and then goes down during the next day. And one can see here that the volumetric soil water layer has a steep increase here, and also there's a temperature drop. So one can safely assume that it rained at this time step. And one can see that the measurement goes down and the neural network ensemble as well. So that might be a hint that it picks up on the physical reality of fires. But to say if there's a causation has to be further. It's just a look at correlation to understand why it's better than persistence. And we also look at longer time series. So this is for Canada. We looked at a fire pixel here from this year, from July to August. And again, in black, we have the measurements, and in red, the prediction. So now it's just for each day, that's one prediction. And one can see here first that the fire-rated power compared to other figures is very large, because this is like very large fire. And the ensemble does not really capture the magnitude of the fire, which is kind of expected because this is a very large fire, and the training set there were not as much large fires like this. So of course the model will be closer to the mean values of the fires. But there's some other things as well you can see here. First, to the size of the fire, you see that it does not go to 0 during the night, and the model captures up. So you see here that it follows the curve of the measurements. And another thing that it does quite well is that it can predict the end of fire. So we trained not on to predict when a fire is starting, because it's highly random and depends on a lot of factors, but we started with, if there's a fire, how will it develop? And you can see here, especially in this one, that it really predicts that the fire goes down at this point. So for future research might be interesting to look at like the exact factors that causes this, but one can already see in this plot that the algorithm can predict if the fire goes out, which Johannes mentioned. There will not be a false alarm, because in the forecast, we have the prediction the fire will go out. We have another example from Greece, which is similar. We see here that the prediction is a little lower, or quite lower, than the actual fire, but it also captures that it does not go out during the night and that it stops at the right time. So we all documented it on GitHub repo with a lot of README files, hopefully make it clear what we did and that it can be replicated, how we trained our models, tested our models, and how you can implement them yourself and get the data. You can find it on the ECMWF Code for Earth site under Fire Forecast. And to summarize, we developed a framework to train and test machine learning models for wildfire forecasting. So in principle, you can add your own model and compare it with the other models. And we also trained an ensemble of neural networks, which produces more accurate forecasts than the current persistence approach. And all steps are documented on GitHub and should be able to reproduce them. We also have an outlook, what can be done in the future. The model can be expanded to include more variables in the training, maybe also increase the size of the data set with data augmentation or some other methods. And the model can also be integrated in the GFAST-CAMS pipeline to actually use it for forecast. And then if it would be introduced in the pipeline, we saw the plot with the pollution here in Bologna. And we at the moment, we tested it with the other GFAST data, but we haven't tested or compared it to real measurements. And the ultimate goal would be to see that using the improved forecast would actually improve the forecasts of air pollution compared to measurements at real stations. So that would be an update. And again, I want to thank our mentors and also Roberto and Xavier, who helped us with technical stuff with like the servers and the GPUs, and of course Atina and Esperanza for helping us doing the coding phase before and after. Thank you very much.